Hey, what's up, Chem 20s? It's Mr. Jukley here, going to talk to you today about concentration of ions in solution. So, the idea with this, like the really big idea with this is, if you were to take an ionic compound, and you were to dissolve it, we know that a dissociation equation is going to happen. We know that it's going to break apart into its individual ions. The concentration of the compound may not be exactly the same as the concentration of its individual ions. So an easy way to think about this is if I had a chocolate bar and it had a whole bunch of almonds on the surface of that chocolate bar, and then if I were to take that chocolate bar and I'll say, okay, I'm going to break it apart into its components, kind of like we do with the dissociation equation. We take a compound and then we dissociate it in water and we break it apart into components or what it's made out of. Essentially what we're going to have left over is we're going to have the chocolate part by itself. How do I move this thing? The chocolate part by itself, and then I'm going to have a whole bunch of individual almonds. Right? So if I'm thinking about this, not in terms of like the thing as a whole, the whole chocolate bar all together with almonds and chocolate, I'm thinking about it more in terms of like, okay, well, I've got this chocolate bar and I've got, in this case, 9 almonds. We are obviously going to have, and I'm going to erase that and draw it one more time, plus 9 of those little almonds. We're obviously going to have way more almonds than we have chocolate. So hopefully that makes sense for people. We'll have a look at it more in the chemistry side of things here. So as we go through and as we look at this, the first thing that we want to do is, well, figure out what the compound is, obviously, and create a dissociation equation. And that's going to tell us, just like with the chocolate bar, we've got one chocolate bar breaking apart into one hunk of chocolate and 9 almonds. Same sort of thing that we've got here. This is going to be one compound breaking into these particular ions. So let's look at that in terms of our actual example number 1 here. So we've got calcium chloride. So first thing I'd probably want to do is figure out what calcium chloride is. CaCl2. Because remember, calcium, just some scrap work off to the side, calcium's got a charge of 2+ when it's an ion, and chlorine's got a charge of 1-, so we need 2 chlorines for every 1 calcium. So let's see, that's going to be solid at room temperature, just like every single ionic compound, and then it's going to break apart into its calcium ions, Ca2+, but it's also going to break apart into its chloride ions, Cl. Each chloride ion is negative, and we have 2 of them. So we're going to use that coefficient, and remember, coefficients are the numbers that come in front. They tell you the entire compound or ion or whatever it is afterwards. So we've got 1 calcium with a charge of 2+, and 2 chlorides, each with a charge of 2-. Cool. So the question is, determine the concentration of the calcium ion and the chloride ion in a solution of 2.4 moles per liter of calcium chloride. So perfect. We know the concentration of calcium chloride. We're looking for the concentration of calcium. So if calcium chloride has 2.4 moles per liter and it makes the same amount of calcium, well, the calcium is going to be 2.4 as well. But let's check this out in the actual mathy sort of view. So our concentration of calcium ions is going to be equal to, let's start with our 2.4 moles for every 1 liter, and we're going to do something very extreme. We're going to say not just 2.4 moles, we're going to say 2.4 moles of what? So it's 2.4 moles of calcium chloride, and then I want to multiply this by a conversion factor. The conversion factor that we're looking at now is called our mole ratio, and it's got to do with our coefficients. Perfect. So you may not even see, but we've got a coefficient, and we don't always write this out, but in front of, and typically we usually don't actually write this out, in front of the calcium ion as well as the calcium chloride, we've got a coefficient of 1. So I'm going to write this out, and you know what? I'm focusing on the numbers too soon. We got to focus on the units first. So I'm multiplying this by a conversion factor. I want to cancel out moles of calcium chloride, CaCl2, because I don't want the moles per liter of calcium chloride, I want the moles per liter of just calcium. So those two, remember things in the top are going to cancel with things in the bottom. So those are totally 100% canceled out. Now I want to have moles of calcium ions. So that's what I want left over. I'm really thinking about these units, and we know that this is a 1-to-1 ratio. So looking at this, it is, get a different color to highlight, 1 mole of calcium for every 1 mole of calcium chloride. So now if I were to look at the units that I have left, I have moles of calcium per liter, which is exactly what I want. I want the concentration of the calcium ions. So I want, let's see, and this is really easy math, 2 times 1 divided by 1, or 2.4, sorry, times 1 divided by 1, just so easy. So that's going to be 2.4 moles of calcium ions for every liter of solution, right? It's exactly the same because 1 calcium chloride produces 1 calcium ion. So not so bad, right? And it's that same thing where we're canceling out units. We don't want the moles of calcium chloride, so we cancel moles of calcium chloride. If it's on the top here, we have to put it in the bottom so they cancel. We end up with moles of calcium. Perfect. So let's try this out with the chlorine. Let's do another example, but let's use chlorine. So I'm going to erase just because I don't have a ton of space here. So let's do the concentration of the chloride ion. So I'm going to start again with what I know. I know I have 2.4 moles of calcium chloride for every 1 liter. Let me just get rid of that highlighting there again. For every 1 liter. Cool. So I want to use my mole ratio. Again, I want to cancel out moles of calcium chloride. So I'm putting moles of calcium chloride on the bottom. So look what happens here. Moles of calcium chloride can cancel with moles of calcium chloride. Perfect. I want to end up with moles of chloride ion. So I want Cl negative on top, and I want that to actually, be moles of Cl negative. Moles Cl negative. Cool, perfect. Now I just have to look at the mole ratio. So what it's telling me here is it's telling me for every 1 calcium chloride that is being dissolved, we end up with 2 chloride ions. So for every 1 calcium chloride that's being dissolved, we end up with 2 chloride ions. So the 2 goes with the moles of chlorine, and the 1 goes with the moles of calcium chloride. So when I go through and I actually multiply this out, I end up with, so let's see, 2.4 times 2, so that would be 4.8 moles of chlorine per liter. And I forgot to put aqueous there. Perfect. So we're using these mole ratios. We're using the idea that you could call it 1 molecule of calcium chloride if you wanted to, produces 2 molecules of chloride. Not really molecules, so it's kind of bad wording there, but hopefully you kind of get the idea. We could take that 1 step further. We could say 1 mole of calcium chloride. So 1 mole of calcium chloride produces 2 moles of chloride. And that is our ratio. And that's all it really is just a ratio. Cool. So let's check out example number 2. And then it's pretty much time for you to do some practice. It should be a nice short lesson here. So determine the concentration of ammonium ion when 55 grams of ammonium nitride dissolves into 350 milliliters of distilled water. This is a significantly bigger question, but we can absolutely do that. The first thing that I want to start with is my concentration, my dissociation equation. So first and foremost, ammonium nitride. So that's going to be NH4 3N. Now I know that it's NH4 3N, so I can show a bit of scrap work over here because I know that NH4 or ammonium has a charge of +1, nitride has a charge of -3, so that means I need 3 positives to balance out my 3 negatives. Perfect. So when this dissolves, we're going to end up with 3 NH4s, so 3 ammonium ions, and 1 nitride ion. Perfect. So there is our dissociation equation. Not too bad. Now this gets kind of big here, right? So I'm starting out, okay, I got 55 grams dissolved in the 350 milliliters. This probably reminds us of some of the stuff that we looked at in the previous lesson there. So I probably want my molar concentration. So I'm going to go through and start with, okay, I got 55 grams, and that's of ammonium nitride. Now this is going to get big. This is going to be a lot of writing here. Please don't be lazy with this. 55 grams of ammonium nitride. So that's NH3, sorry, NH4, 3N. Now I'm going to multiply this by something that's going to give me the moles, right? So what could I multiply this to give me moles? Well, it's my molar mass. So we got to put our video on pause for a second. We got to figure out our molar mass of ammonium nitride. Okay, nice. So if you haven't already put it on pause, you can go ahead and do that. Now, if you got 68.16 grams per mole, you're spot on. So what I want to do now is I want to multiply this. So I'm getting rid of grams, and in particular, it's grams of NH4, 3N, so that's our ammonium nitride. And I want to end up with moles of NH4N. Perfect. So grams of this whole thing cancels with grams of that whole thing. Now I know that it is 68.16 grams for every 1 mole. So if we were to stop right here, if we were to put the brakes on, we could go through and we could say, okay, well, what do I have left? If I were to do this calculation, I would have the moles of ammonium nitride. Sweet. We don't want the moles of ammonium nitride. We want the concentration of ammonium nitride. So knowing that concentration is moles per liter, I essentially just need to multiply this by a conversion factor where I get liters in the bottom. So it's going to be 0.350 liters. And now if I were to look at the units, the one's just kind of a placeholder here saying that we're dividing by liters. I've got moles divided by liters. Cool. Those are the only units that are left. And in particular, it's moles of ammonium nitride. Now I need one more little thing here because I'm not looking for the moles of ammonium nitride. I'm looking for the moles of just the ammonium. So again, I need to go through and I need to say, okay, well, all the way up here on the top where I just put this red underline here, I've got moles of ammonium nitride. If I wanted to get rid of that, I'd better put that on the bottom. So moles of NH4, 3N, and then I want to end up with, the point of the question is to figure out my ammonium ion. So I want moles of NH4 plus, or my ammonium ion. Now I go back and I look at the mole ratio. It says I've got 3 NH4s for every, and it doesn't actually show it here, for every 1 ammonium nitride. So I know that I have 3 NH4s for 1 ammonium nitride, and I know that my moles of ammonium nitride are going to cross off with my moles of ammonium nitride. What are the only units we have left in this whole thing right now? The only units, we have moles of NH4 per liter. Perfect. That's exactly what we wanted. So when we go through and we plug this in, I'm going to do 55 divided by 68.16 divided by 0.350, and then times 3. Because remember, multiplying by 1, dividing by 1 doesn't really matter at all. So I think this actually works out to be, and with proper significant digits, 0.692 moles of NH4 per liter. And I forgot to switch the color back, so we're in a big old red red marker there. Perfect. So again, the whole kind of key with this is make sure we're canceling out units to get what we want. Now this is a challenge to start. Absolutely 100% a challenge to start. But can you do it? Yeah, totally. Absolutely. And we can even break this down a little bit further. Let's go through and let's just pick a nice color for this. Essentially what we did is we used N is equal to mass divided by molar mass to solve for N. That was our first step. And we use C is equal to N over V. That's sort of our second step in here to figure out a concentration. And then we used, again, that mole ratio to figure out the concentration of the other thing. Cool. So that is about it for today. This is going to take some practice. Absolutely. You can look up some other videos on YouTube. But really all it comes down to is canceling out units. Please try it out. You've only got like 6 questions here, I believe. Please try it out. This is also really, really, really important as we move forward. This is the entire stoichiometry unit. If you can do this now, you can do the entire stoichiometry unit. We'll build up, obviously, and we'll talk about this. But anyways, that's it for now. I better go actually meet with you, Chem 20s. Okay, talk to you later. Bye for now. Bye for now.